Done, ma'am. Kindly proceed.
Live streaming?
Yes, sir.
Yes,
Okay.
sir, it shows. So good afternoon, everyone, to the weekly online lecture series on atmospheric dynamics and its applications to climate sciences, which is jointly hosted by South Asian Meteorological Association, SAMA, and Savitribai Phule Pune University. Today's lecture will be delivered by Dr. Aditi Deshpande, who is a faculty in Savitribai Phule Pune University, Department of Atmospheric and Space Sciences. But before that, we will wait for the welcome address by Professor Someshwar Das.
Okay. All right. Thank you so much, Dr. Rohini. Professor Ajit Tyagi Saab, President of SAMA. Dr. Aditi Deshpande, today's distinguished speaker. Our colleagues, the members of the organizing committee, Dr. Rohini, Dr. Divya Prakash, Dr. Mohan, and also our EC member from Myanmar, Dr. Kya Duin U. I welcome you on behalf of the South Asian Meteorological Association and Savitribai Phule Pune University, India. As you know, this is the 5th lecture series on atmospheric dynamics and its applications to climate sciences, being jointly organized by SAMA and SPPU for capacity building of the people of South Asia and the member countries of the non-aligned movement, NAM. This is the 9th lecture of this series of lectures on atmospheric dynamics. The syllabus of the lecture, as you know, has been designed based on the feedback and requirements of the member countries of SAMA. This lectures series is targeted at postgraduate students and professionals of non-meteorological backgrounds who are interested in learning atmospheric dynamics and its applications to climate sciences. This lecture series will continue for about 6.5 months, about 26 weeks, and it started from 18th of January till 2nd of August. It is supposed to continue. As on today, about 1,145 people have registered from about 50 plus countries for this lecture series. And although we have not closed yet, but I think this is the final number. Probably nobody else may register now from now onwards. Only today is the 9th lecture. As mentioned in the beginning, many earlier also in earlier welcome addresses, that the prerequisite for this course is that one should have a very strong background of the physics and mathematics, and this course itself is a prerequisite for learning numerical weather prediction. Okay, so all of you are requested to put attention to the lectures. Those who have missed the past lectures can always view it on the YouTube. It is always available. The current lecture also will be available on the YouTube, and this will be useful to you for your final exam preparation. As you know, this is a bit a tough subject for many people, so you have to be very, very attentive in hearing the lecture, and also you can interact with the speaker today if you are attending live. You can write your questions in the question box, and it will be answered by the speaker at the end of the lecture today. So we shall try to have as many interactions as possible between the participants and the speaker. Okay, so enjoy the lecture and have a nice day. On to you, Dr. Rohini.
Thank you, sir. Now I would like to introduce our today's speaker, Dr. Aditi Deshpande. Share my screen. So Dr. Aditi Deshpande has completed her MSc in physics from Mumbai University and then went on to complete her MTech in atmospheric sciences from the Savitribai Phule Pune University. She did her PhD from Indian Institute of Tropical Meteorology, Pune, and joined as an assistant professor in this department, which is our Atmospheric and Space Science Department in Savitribai Phule Pune University in May 2016. As an early career researcher, she has 2 ongoing projects from DST SERB and SAT, and also from ISRO. And she has published more than 8 peer-reviewed papers and 1 book chapter. She has guided over 14 MSc and MTech students and is currently guiding a PhD student also. Aditi has always been interested in atmospheric sciences since her BSc days and further got interested in ocean dynamics and ocean circulation, which she pursued during her PhD. She is currently working on Arabian Sea circulation and is interested in studying the global ocean circulation changes and their impact on our climate in the ocean warming environment. She is also working on ocean biogeochemistry and its link to ocean dynamics and has worked on Indian summer monsoon variability. She is also interested in ocean conservation and the interaction of climate policy and climate justice. I'm very happy that Aditi is also teaching number of courses in our department, that is dynamic meteorology, oceanography, climate sciences. So I would request Dr. Aditi to please deliver her lecture. Thank you.
Thank you so much, Dr. Rohini, for that introduction. And I want to thank SPPU and SAMA for giving me an opportunity to present this one particular lecture. It's a very crucial topic. I'm going to try and share my screen. I hope everyone is able to see my screen.
Yes, we can
Yes.
see your screen.
Okay, so at any point of time, if my voice falters or if there is any issue, please let me know. You can stop me in the middle so that there is continuity in the lecture. And yes, this is a wonderful series of lectures that SAMA has organized. I know I am a junior colleague of Dr. Rohini Babar. I know how much running around and effort she has put into getting all of this together. And it's a really commendable series to educate students who are interested in the subject, but they may not have a formal course. So we are going to today look at the concept of divergence and vorticity and their expression in different coordinate systems. Now, I'm going to start with some basics like the definition of divergence. What does divergence mean? In dynamics, divergence refers to the rate at which air is spreading apart from a particular point in space. So as you can see, someone please let me know if the laser pointer that I'm using is visible to everyone. I hope to the participants as well. So it's a small schematic to show that, you know, if there is a region where over the surface or at any level in the atmosphere, if there is air which is spreading away from that region, that particular phenomenon is called as divergence, and it's given by a simple equation which is del dot of velocity, where you are looking at the horizontal component of velocity. So here we have written du by dx plus dv by dx, dv by dy, and you can see that the unit is per second. Vorticity, on the other hand, is a microscopic measure of rotation of a fluid, and it is a vector which is defined as the curl of velocity. So here it is, I think I made a mistake. This should be curl of velocity, not zeta. Zeta is essentially the symbol which is most commonly used in most textbooks to denote vorticity, and absolute vorticity is the curl of absolute velocity, and relative vorticity is the curl of relative velocity. This is basically, these two lines are definitions which are taken from Halton, and I will encourage and suggest that all students specifically read Halton as a as one of those books which will teach you everything about dynamics. So if you do not have access to Halton, find friends, find ways of going to a library and look up Halton and make sure that you read it inside out. Okay. Moving on, so if you were to compare these two images, you can see that this is essentially air which is sort of moving out of an area, and this is somehow measuring how much the air is turning within a region. Now, if we were to give like a visual representation, this is what it looks like. So at every step of every point on the grid or every point of the rotation, if you want to measure how much rotation exists, that is what we are looking at in terms of vorticity. Whereas divergent motion is this. Essentially, it is going out of the region or whether air is coming into the region. So divergence has both positive and negative components. We'll come to that in a bit. There are different types of vorticity. So like I said, the definition said that there is absolute vorticity and then there is relative vorticity. Absolute vorticity, like it shows over here, is essentially addition of relative vorticity and what is called as planetary vorticity or vorticity of Earth, which is denoted by the Coriolis force F. Not force, but the symbol F. Relative vorticity is a curl of wind, horizontal wind that we are taking. So we are looking at dv by dx minus du by dy. So if we were to write this in terms of absolute vorticity, it's a combination of planetary and relative vorticity. Now, unless you are looking at a specific system that is moving through the latitudes, one can actually think of changes in F in certain phenomenon as either being small or we also have to take into consideration our calculations, how F varies through each and every latitude. But in spite of that, having said that, vorticity is a conserved quantity. So at any point of time, our absolute vorticity or d by dt of zeta A is always conserved. And one more concept which is important in vorticity is called as potential vorticity. So instead of taking the rotation at each level separately, if you look at the atmosphere or the ocean for that matter as a column, and you're measuring its vorticity at each point, you also have to take into consideration the height of the column, which is why this vorticity conservation equation that you see over here says zeta plus F by H. So this H is basically the depth of the column that we are considering. This basically comes in relation to, in Halton, it comes somewhere close to where shallow water equations are discussed. And it shows that the whole quantity as such is conserved. So d by dt of this whole quantity goes to 0. Now, vorticity is something which is very strongly and very inherently linked with circulation. In atmospheric dynamics or in Earth system sciences, we always look at circulation as something in a closed loop or a closed circuit. I want to, if someone were to ask that, does any kind of flow have vorticity? Then one need not necessarily know if every kind of flow will have vorticity. But where there is a circulation in a closed loop or where air turns in a specific direction, there, of course, you will have vorticity. And vorticity and circulation is linked through various theorems. Now, one of the main theorems is the Stokes theorem, which says that the circulation around a closed curve is given by the area of the product of the area bounded by the curve and the vorticity normal to the area. So just going back for a second, when we look at this particular equation, what you're looking at is how much the the air is turning horizontally. But here, when we are looking at the vorticity, we are looking at the vorticity normal to that area, and we are looking at the product, the area bounded by the curve. So you can have any possible sort of flow. It need not be, in a very specific or in a very clear-cut circle or in a closed loop. It can have a different kind of flow, but as long as you're looking at a closed circulation, the Stokes theorem actually applies vorticity in order to understand how the circulation can be measured. Then there is the Biochny's circulation theorem, where it says that the rate of change of absolute circulation around a closed curve is equal to the solenoids enclosed by the curve to which this circulation refers. And it is essentially a sort of a combination of Kelvin's theorem applied to Kelvin's theorem and equations of motion. So the Kelvin's theorem says that if you have a closed circulation, the acceleration due to circulation is equal to the circulation of acceleration. It sort of sounds like a tongue twister, but it's once you apply this particular loop to your momentum equations, what you get is Biochny's theorem. And we also have something called as positive and negative divergence. So when we define divergence as du by dx plus dv by dy, that is what is called as divergence, where air is moving away from a specific area, but air can also move into a specific area. So for example, if I go back to my slides where you see this particular region and it says an L, which in meteorology most often is denoted as a low pressure system, you can understand that there will be air moving into or towards the low pressure system from a high pressure system. And here the manner in which it turns or it rotates, that measure can be given by vorticity. Now, this is how positive and negative divergence and convergence actually looks like. And if I were to look at how vorticity, or for that matter, divergence, can help us understand how circulation takes place, like, for example, why do winds turn in a specific direction, or what kind of weather systems can change or move around based on changes in vorticity, changes in relative vorticity, or changes in absolute vorticity, and how or what happens, or how does the system sort of rearrange itself in order to maintain that conservation of vorticity. We can actually understand that by looking at the vorticity equation. Now, I know that the term say the lecture title said that we are supposed to look at it in a different coordinate systems, but I've stuck to only 2 over here, simply because it is important to understand the concept of what vorticity, or how vorticity and divergence manifests in the atmosphere and in the oceans, rather than just looking at equations. So this particular equation that you're seeing, we see about 3 terms on the right-hand side. This is simply, if you take the U momentum equation and the V momentum equation, and you remember what the definition of vorticity is, which is, I had written this somewhere, sorry. dV by dx, yes, dV by dx minus du by dx. So you take the V momentum equation, take a derivative by x, take the U momentum equation, take a derivative by y, and subtract one from the other. And when you pull together similar looking systems, you get what is called as the vorticity equation. Now, here always see that it is always mentioned that there is zeta and f. So this is your relative vorticity and this is your planetary vorticity. And this is again your absolute vorticity. And if you remember the definition of divergence, this gives divergence. So this is basically minus zeta a d. D being this particular D where it stands for divergence. Then there is this tilting term, and then there is a solenoidal term. So this comes from your pressure gradient and this comes from your vertical wind. Now, all of these terms, or rather each of these terms, will dominate during certain systems or certain circulations. And it actually helps us figure out in what manner a flow is going to progress, provided we understand how we go through the specifics of how your winds are, or we have good measurements about for each of these systems. In an isobaric coordinate system, this is what the equation looks like. I'm purposely not going into the derivations because most of this is given in Halton's book. And I am a little old school. I believe in encouraging students to actually sit down with a paper and a pen and try to derive it yourself. So I encourage all of you to actually sit and derive, because it's fun to do that. And when you derive it yourself, you'll actually understand how there are certain times when, because certain systems are coming together within these equations, it actually gives us an idea of how these systems manifest in the real system as well. The divergence equation is not as clean as what you see in the vorticity equation, simply because now remember what divergence definition is. It is dv, it's right here, it's du by dx plus dv by dy. So you take your momentum equation, derive it by x, take your v momentum equation, take a derivative by y, and then add it together, and then through some mathematical permutations and combinations and manipulations, you will come to this particular equation. Now, all of this is about how these equations are derived and how they come about. But how do they actually manifest in the atmosphere? What does it mean to see divergence in, say, atmosphere or in a real system? Well, that is something which all of us have known for a very long time. So basically, when you look at the vertical structure of the atmosphere, if you have negative divergence, or that is convergence at the surface, most often very close, in the upper atmosphere, you will see divergence. This is because mass is conserved, and then if something is coming together at one level, at another level, there will be divergence. And if there is divergence at surface, there will be convergence at the top. This is something that you see very often, or something which is very familiar to almost all students of meteorology and also of physics that we see in general circulation. So if you look at the winds, these are surface winds, what you see within the circle, and what you are looking at is essentially the vertical section of what the column would look like. So if you look at the tropical region, and specifically over the equatorial region, what is happening is that winds come together from either of the hemispheres, called as the trade winds, or northeasterly and southeasterly winds. They converge at very close to the equator, and they rise up in the sky. So this is a region, this is the surface where convergence is happening. And because there is convergence, there is air coming towards the equator, it is rising up, and somewhere in the upper atmosphere, you see divergence. So if you were to take a sort of a cross section of this region, this is what you'll see. You are looking at how air is coming together in one region. And if you keep going upwards, you will see that it is diverging in the upper air. Also, even within the surface region, so given at one particular level, what you will see is you have easterlies in the tropics and you have westerlies in the subtropics. This is known to everyone as the model of general circulation. And you will see that winds are, if you look at this particular region, close to the 30 degrees, both north and south, winds are moving easterly and your winds are moving westerly, which means there is divergence in this region also. So at any given surface also, you can see divergence within this region. And at each of these levels where you see, this is where your wind air is sort of diverging at the surface, but in the upper air it is converging. Whereas in the tropics, it is converging at the surface, but in the upper air it is diverging. It's also something that you see in multiple meteorological phenomena. Now, how do we look at vorticity in a physical system? How do we visualize it? And because I come from an oceanography background, I thought this was a good opportunity to show our students how vorticity conservation applies, or how it has helped us understand a very unique thing that happens in the oceans, which is called a subtropical gyre. So this is actually a figure of the Atlantic Ocean, North Atlantic Ocean. And you see different currents over here. But what I want you to look at are these two. There is the Gulf Stream, and here there is the Canary Current. Now, if you look at the Gulf Stream and any kind of current in the western side of the ocean, so you keep yourself in the, let's say you imagine yourself in the center of the ocean, and to your west is where your Gulf Stream is sitting, and to your east is where the Canary Current is. All the currents on the western end of the oceans are supposed to be extremely swift, very strong, and very deep. Whereas the currents on the east side are sluggish, they are shallow, and they are they are not streamlined quite like what you are looking in the Gulf Stream over here. Now, this has a lot of implications, because if these Gulf Stream, and you can see that the Gulf Stream is a current which moves from surface to the from the tropics to the subtropics. So it is essentially taking warm water or heat. It is transporting heat from the tropics to the subtropics. And Gulf Stream has a lot of implications for how weather is suitable or rather survivable, not just in the subtropical region, but almost all across the European region. Now there is, I just want students to remember this. This is something which is seen in all of the basins across the globe. So you have a subtropical gyre in the North Pacific. There is one in the South Pacific. There is one in the North Atlantic and South Atlantic. In the Indian Ocean, you have the subcontinental landmass sitting in the north. So you don't have one in the north, but you have one in the south. And this has been actually, these western boundary currents have been a subject of study for a lot of oceanographers, and not just for oceanographers. I'm sure everyone will recognize this particular picture from media. It's a scene from Finding Nemo. And if you remember, these turtles sitting behind, they are actually moving across what is called as the East Australian Current. Now, the East Australian Current is also a western boundary current in the southern hemisphere, and it's a very strong streamlined current. And it is, in fact, why is it that we have all the western boundary currents so strong and all the eastern boundary currents so sluggish or shallow? The reason for that is conservation of potential vorticity. And because the winds are actually supplying momentum to the oceans, and that is how the surface currents move, these subtropical gyres have so organized themselves so that potential vorticity within each of these basins is conserved. I'm sure that there are multiple examples of how potential vorticity gets conserved even in the atmospheric system. So, for example, if you look at the cross-equatorial jet stream, which is seen during monsoon over the which brings rain to the Indian subcontinent and also to Bangladesh and other South Asian countries, the reason why it turns the way it does is not just associated with Coriolis force, but why is it or rather the depth at which, the height at which it extends to, plus how it turns, all of that is determined by conservation of vorticity. Additionally, why do cyclones move in a particular direction in the northern and the southern hemisphere? And how do cyclones sort of move in a specific direction? Which route do they take? All of that depends on conservation of absolute vorticity. So vorticity is something which is very inherently linked to any kind of circulation within our system. And I have not spent much time on explaining what vorticity and divergence is. Divergence being a relatively simple concept, but vorticity takes a little bit of time to get used to. We just have to understand that any kind of circular system that you see, or the circulation that you see, it is essentially measuring how it's sort of a way to quantify the rotation of that particular system. And that is why in every kind of flow that you see on our planet, whether it is in the atmosphere, whether it is in the ocean, the manner in which our circulation in the atmosphere, the general circulation is sort of organized, the gyres are organized, all of that has a dependency on how vorticity is conserved. So I want to spend more time on question and answers. So I'm hoping that students ask more questions. So please continue asking questions, and I'll try to answer them to the best of my ability. Thank you.
Thank you, Dr. Aditi. Before we go to question answer session, we would take a picture. So Tyagi sir. Yeah,
Ronnie, I am there.
yes, sir. Who is in DMH Myanmar? Yeah, you would like to. Sir, you're muted. Das sir, you're muted.
I think Dr. Kyamo be also signed in, logged in, but
Yeah,
he's
he's
not.
there.
No, Dr. Kyal, who is there, but
Yeah.
the DG also probably is there, but he is not visible.
Yeah. So Ashwin, yeah, you can take some pictures, and we can circulate in the SAMA group.
Thank you.
Thank you, Ashwin.
So I would request now Mrunal to please moderate the question answer session.
एक बार बताइए, जैसे अभी तो मेरा जो भी पैसा आता है पेटीएम के थ्रू, वो ICICI बैंक में जाता है।
डिफॉल्ट किया हुआ ना आपने।
अच्छा,
Jaggi sir, please
Report.
mute your mic.
Yeah, I think there are no questions have been typed till now. So
Okay.
participants, I would request if you would like to type your questions right now.
Okay, till then, I'd like to tell everyone that the chapter number 4 in the 5th edition of Halton is where most of this material from today's lectures is taken, except for the ones related to ocean circulation that is given in Robert Stewart's book. And that Robert Stewart's book, at least the last I checked, was openly available, and it gives a very beautiful description of how conservation of absolute vorticity works in the subtropical gyre systems. So I encourage everyone to please look it up, and I have given my email ID to everyone, and if you have any questions, please feel free to mail me as well.
So there is one question. How the ocean currents affect ENSO? Can you suggest standard books for oceanic circulations?
Sorry, I was muted. ENSO is essentially a system. The full form is El Nino Southern Oscillation. It is a system that it is a phenomenon that occurs in the equatorial Pacific, and simply because the Pacific is such a large basin, any system which happens in the Pacific sort of has repercussions across almost the entire globe. So ENSO tends to affect weather and climate across the entire Asian continent, as well as in America, as well as in South America. A very good book to start off with is the one I mentioned, Robert Stewart's book. I think it's called Introduction to Physical Oceanography. Last I checked, it was freely available online. There is also another book called Regional Oceanography by Tomczak and Godfrey. Again, it is available, freely available online. And I took the picture of that Atlantic Ocean from that book. So it gives a very good description of how currents work, how the theories that determine why currents work in a specific manner or why they flow in a specific direction, and how ENSO occurs. That is given, I think, in Robert Stewart's book very well. But there is also an entire book dedicated to El Nino Southern Oscillation. So I encourage you to look it up. There will also be a lot of lectures given on ENSO, because ENSO is something which is very important for our climate, and it is undergoing a lot of changes because of climate change.
Yes, thank you, ma'am. So there is another question by Savi Naidu. How does vorticity influence on trade winds?
Okay, so if you look at how winds turn, that comes under the influence of Coriolis force that is acting on wind. So any object that moves on Earth, because Earth is rotating, it comes under the influence of the non-inertial system. But vorticity doesn't influence. Vorticity is actually a measure of the turning. So if you are to look at, say, you look at a section of trade winds and you try to, if you want to say, see how much the winds are turning, a good measure is to look at the relative vorticity, that is dv by dx and du by dy. So you take your meridional component of the wind and you take the zonal component of the wind and you use the formula, and that along with your Coriolis force will give you a measure of how much the winds will turn. So it's not so much as an influence, but more as a measure. It's a quantity that you can actually calculate.
Yes, thank you so much, ma'am. There are no more questions. If participants do have questions, please type them in a chat box. Yeah, so now I request
So thank you, Mrunal. Before going to, this was a very short lecture, nice lecture. So I would request, before I request Ashwin to give vote of thanks, I would tell you the statistics for today. So around 125, 27 participants have registered, recorded their attendance, out of which around 102 participants have rated it as excellent or good. And out of that, all the 125 participants or so, 69% are students, 27 are employees, and the rest are scientists or faculties. So most of the part is students.
Okay, Dr. Rohini, if you allow me, I see one question by Surya on
Yes.
cyclones. Yeah, so yes, they. I'm not saying that they form. Okay, this is something that will take a little bit of getting used to. You know that cyclonic circulation is basically circular. So you have a low pressure system and wind tries to move from high pressure to low pressure. And because we are on a rotating system, it turns. Now, that turning of the winds will have some level of vorticity, which we call as relative vorticity. So any kind of circular movement, any kind of turning of winds will have some level of vorticity, and you have planetary vorticity. Now, the entire the value of what, or rather the entire vorticity has to be conserved. So how much cyclones turn, which track they will take. So for example, if you're in the northern hemisphere, you will see that quite a few cyclones, if they are evolving and intensifying not very rapidly or in a theoretical sense, they usually move in the northwest direction, because it depends on the Coriolis force. Now, Coriolis force plus the turning of the winds, which can be measured using the formula and calculating relative vorticity, that entire thing has to be conserved. Which means that together a cyclone, the turning of the winds and the movement of the cyclone within a specific basin will have some conserved value of vorticity, absolute vorticity. That is what happens. So the formation of a cyclone is a different process altogether. It requires moist energy from the oceans. It requires a specific level of instability in the atmosphere. And it also requires enough continuous supply of moist energy in order for that cyclone to evolve. But the dynamic part, which is the turning of the wind part and its measurement, that is what the absolute vorticity is conserved together. Okay, I hope I was clear. Vorticity measurement from satellites be used in real time. Okay. Again, vorticity is a value which is calculated. So you will have winds from satellite measurement or any kind of measurements, and you can have the value of vorticity that you can calculate. Okay, what is the relationship between eddies and vorticity? Okay, so I'm assuming that you're talking about eddies in the ocean. If not, you can type again. But eddies are essentially systems which are, so if you have a flow in a particular direction, there will be some form of meandering of the flow. It's very rare to see a very streamlined structure being continuous and for a long, over a long distance being very, very streamlined. So all of these meanders, they occur in the form of eddy-like systems. Now, eddy-like systems in themselves are circular in direction. There can be either cyclonic or anticyclonic eddies or anticyclonic circulations, and these eddies will have vorticity again because they are turning. They have a curvature. They are a closed loop system. So yes, they will carry some value of vorticity. Now, how it is conserved and all of that, that again depends on how you look at whether it is a meridional movement or whether it is a zonal movement or whether they are stationary eddies. All of that will figure in its calculation of vorticity. Okay. What are the vorticity limits quantitatively we observe for cyclones and other gyres? That is a very difficult question to answer, because cyclones are, you don't see the same kind of cyclone everywhere. So if you are to look at two cyclones occurring over a same region or evolving over a same region, they will still be very different because the conditions for their evolution will change. The manner in which they evolve changes, how their tracks change. if that was not the case, let me tell you, cyclone forecasting would be very simple because you will have one model and you know that you can plug in something and you will get a track of every cyclone that can ever happen. But that is not the case. So I'm not sure if there is a specific value of vorticity that cyclones have. I have not really calculated, but you can take that as a what you know personal assignment if you are that interested. Most of your data is available on multiple meteorology websites, even for cyclones. So you can take the values of U and V and you can calculate what kind of vorticity values are there at maybe one particular level that will give you a value. The gyres again, because they are, if you're talking about the subtropical gyres that are showed in the oceanic system, they are large scale gyres. Again, the gyres are formed by currents which are sort of moving across the basin. So they themselves have their own variability. So I'm not sure if there is like an average value of vorticity that we consider. There might be, but I am not aware of such a value as such. What role does vorticity play on jet streams? Okay, so less about vorticity and more about vorticity conservation. So jet streams, if you look at, let's say, the polar jet stream, which is somewhere very close to 60° north, whether it moves or it meanders to the southern latitudes or it stays very close to 60° north will depend on its vorticity conservation as well. And that whether it meanders or not, that is driven by, of course, other forces, but how much it meanders and how much it will turn, that will be dominated, or that will be sort of driven by vorticity conservation overall. So I hope this was useful.
Yes, thank you, Dr. Aditi. So now I request Ashwin to please give vote of thanks.
Thank you. So on behalf of organizing committee, I extend my sincere thanks to everyone who contributed to the success of 8th lecture in our weekly online lecture series on atmospheric dynamics and its application to climate sciences. So we are especially grateful to Professor Someshwar Das, Secretary SAMA, for his warm welcome address and insightful overview of this lecture series. My heartfelt thanks also goes to our distinguished speaker, Dr. Aditi Deshpande from SPPU, for delivering an enlightening lecture on concept of divergence and vorticity, their expression and in different coordinate systems. I would like to acknowledge Dr. Rohini Bhavar for moderating the session and Ms. Mrunal Naik for efficiently managing the question and answer segment. Additionally, I appreciate the guidance and support of all the panelists and EC members who ensured every detail was impeccably arranged. A special thanks to all participants and attendees who joined us from across the globe, and to the dedicated team members at Savitribai Phule Pune University for their invaluable role in organizing this lecture. Thank you. Thank you so much.
Thank you, Ashwin. The revised statistics, 150 participants have attended, out of which 126 have given it as excellent or very good. Of course, the number of students is large in that. So the next lecture will be on 22nd March, same time, and it will be delivered by Dr. A.K. Sahai, who is retired scientist from IITM. And the topic will be equation of continuity in Cartesian and isobaric coordinate systems, Dien's compensation principle, concept of level of non-divergence. We will also be sharing today the one problem assignment from today's lecturer, Dr. Aditi, on Monday. And please, everyone, we request you to write in the subject. The assignment is for which lecture series in the subject itself, as well as please send it before the next lecture, because if the participants keep on sending it even in the continuing weeks, it will be difficult for the speaker to evaluate it. So if you can finish the assignment in that 4 or 5 days and send it, it will be really great. Tyagi sir and Someshwar Das sir, any more comments or suggestions? Or
Okay, well, thank you so much, Dr. Aditi, for your lecture. In fact, of course, somehow we cannot see the participants face to face now in this mode because this is a Zoom panel mode. But from the questions, I'm sure that the kind of questions they have raised is very, very fundamental, and probably they are not very much aware of the subject. I mean, somehow they were trying to connect Vorticity with whatever things they know. Now, I hope that you all know that the divergence and vorticities are the most important parameters for the development of any weather system in the atmosphere. For example, if there is a divergence, what kind of weather do you expect? You know that? If there is a divergence, then the weather will be clear. And also, the sign of the divergence and the vorticity. Do you know what is the positive vorticity means, or what is the negative vorticity means, or what is the positive divergence means, or what is the negative divergence means? I think that most of you may not be aware of it. Negative divergence is convergence. I hope you know. Positive divergence is divergence. I hope you know. But from the kind of questions people have raised, it seems that they are not even aware of those things. Similarly, the positive vorticity means what? Cyclonic circulation. Negative vorticity means what? Anticyclonic circulation. Probably many of you do not know even that. You are asking questions about impact on the ENSO, impact on the jet stream, I mean, trade wind, etc. They are different things. First of all, you should learn what is the concept, the fundamental aspects of the divergence and vorticity, right? And also, you should know that when we say positive vorticity is cyclonic, that means that is in the northern hemisphere only. It is opposite in the southern hemisphere. Okay. And so also is for the divergence. The sign changes or reverses between northern and southern hemisphere. Okay. So if there is a positive vorticity, somebody is asking what is the magnitude of the vorticity in cyclone? Well, what is the magnitude? First of all, are you aware of what is the order of the typical order of the vorticity? Probably you may not be aware. What is the typical order of the vorticity? Vorticity is a very small parameter. Its order is about 10 to the power minus 5. Do you know that? The order of the typical order of the vorticity is about 10 to the power minus 5. Okay. So if it is a very strong vorticity, a strong positive vorticity, it could be 10 to the power minus 4, but that is a very, very strong vorticity. Okay. And in the cyclone, again, depends on what stage we are talking about, whether it is just a deep cyclonic circulation, depression, okay, or just a formative stage, or a moderate cyclone, or a very intense cyclone, or a super cyclone. So the intensity of the cyclone will determine what is the vorticity. Okay. Vorticity is definitely very, very important. But then the formation of cyclone does not depend just on one parameter. Okay. I mean, there is again a separate subject in itself. So anyway, it was a good talk, very fundamental talk, and I hope all the participants course. And if you still have questions, you are all welcome to ask your questions through the email also. There is no problem. Okay. So that's all from my side. I think Tagis have not spoken anything. So maybe Tagis can say something.
Somesh, you have summarized the key issues related to these vorticity and vergence, which are fundamental for the dynamics of our atmospheric circulations. And I request all participants to delve into these, and could be that we could provide some handout on this topic so
I
that
think I can give that Halton chapter which discusses Vorticity. That one particular PDF I can send to the students.
yeah, that would be good.
So that will be, because
Yeah.
Vorticity is a concept that takes a little getting used to. I understand that.
Yeah, true,
So
true.
let students read, and like I said, my email ID was given in the PPT. So y'all are free to mail me at any time. I'd be happy to answer your
Thank you
questions.
so much. That's what this series are there, that the resource person should be accessible and they are responsive, so that it gives the strength. So my request to all participants, and I'm thankful to see you agreeing to provide the Holton chapter, so that will clear the concept, and they can get in touch with you for further clarifications. Thank you, Aditi.
Thank you for the opportunity to sum up.
Thank you, everyone. So now if we are done with today's lecture, so I would, with permission of Tyagi sir and Someshwar Das sir, can we end the meeting?
Please do that. Please do that. Thank
Yes.
you, Ronnie. And
Thank you, sir.
team of your SPPU was great going.
Sir, I wanted to ask now how to send these assignments for evaluation also. We should have a meeting probably for this.
Okay,
Yeah,
Maybe
maybe
not now, maybe,
let the
but a quick
so
not now. Yeah, not now.
how many
Or
assignments?
we can
combined
always
for
in fact,
lecture 7 and lecture 8, around
is the third one,
200
I think,
assignments
right?
are there. So 100 each.
Oh, even received number of
Yeah,
people who have
100
submitted
each,
the assignments, right?
100 each for lecture 7. And what is happening, that is why I told the participants to please send in the same upcoming 4-5 days, because they are still sending the assignments for lecture 7 and lecture 8. So it will
No.
be so much of
No.
confusion, sir.
If can I give a suggestion, Dr. Rohini?
No,
Yeah,
let them be clear
Das
that
sir and Tyagi
let
sir's
them be clear
permission.
that
If you have a Google form where it is let's say Monday the assignment is given, and Friday or Saturday morning you stop taking replies from that form, then within that week whatever you get is the assignments, and they can upload whatever, whether in written form or online form, whichever form they want to provide it, they can upload their answers that way. So you will have a handle on not being overwhelmed with the number of replies every week, and then that way you can give some
Right.
timeline to all the instructors also, so then that way we can.
Yeah,
Yeah,
this we were planning to do it since this lecture, but I'm talking about lecture number 7 and 8, which has like 2 problems, 1 short answer, 1 problem, and 3 multiple choice. So the assignment is big for lecture 7 and 8, and how to.
It all, yeah, for 7 and 8 also, do not consider the, I think, answers which have been submitted after the deadline. But we
After
said
the
that
deadline.
clearly. Yeah, you submit your, I mean, they will not get any score for that, right? I mean, they can submit, that is a different thing, but they will not get. And as Dr. Aditi has already said, if you're submitting the answer through Google Sheet, then you can always set a deadline, and after which it will not be accepted anyway.
Yeah, that we were planning to do from this lecture, like only 1 problem, right?
From this
1
lecture only,
short answer or problem.
yeah, only 1 problem, and preferably a numerical problem.
Yes.
And through the Google form, so that people can write clearly their name, their country, their affiliation, and everything. Otherwise, they're not writing those things probably, I think. So now those answer sheets which have been submitted already, yeah, I think we can ask some of the student coordinators or your students now who are not attending this course, maybe they can download the answer sheets, because downloading 200 sheets also, it is a
It's a
big
big
task
task,
for the
sir.
evaluator.
Yes.
For any evaluator, downloading all the answer sheet will be a big task. It will be easier, in the Google form. That's why. So anyway, for 7 and 8, somehow we have to take the help of some students to download all the answer sheets and put them on your Google Drive and give the link to the evaluator, so that he doesn't have to download the answer sheets. he can directly click the link and then
So we can give that mail ID
evaluate
also
that.
if they want. Because it will take a lot of
Yeah,
time,
mail
otherwise
ID,
downloading separately each.
yeah,
Maybe this,
whoever is downloading,
Zip it and mail it as
that
a
you have
zip
to
file.
share the mail ID. Yeah, whoever is downloading the answer sheet,
yeah, we can share mail ID and password with them. Whoever, like few students, a group can be there.
yeah, share the mail ID.
Because we already
with
have
them.
the solutions, so no problem.
Yeah, whoever is, yeah, right.
Tyagi
So
sir
some
wanted
labor
to
job is
say-
there because we have just started from 7th lecture onwards, but yeah.
Tyagi sir wanted to say something.
Any suggestions, sir?
No,
Tyagi sir?
no, yeah, yeah. See, for any resource persons to go through 100 or 100 plus answer sheets, we are asking too much
Not
from
audio.
him. Am I audible?
Yes, sir, yes.
Yeah.
So
Yeah.
we have now come to one simple problem, that is that only one questions, which is if is numerical, then it is good. Otherwise,
Yeah.
short answer type. So that
Yeah.
would be there. And we could have if the reply answer is standard answer to that, then it can be evaluated by students also.
PhD students, maybe.
Yeah. So we can't load. Let's see how Aditi can manage, and her feedback about one question's response, or whether it is manageable or not manageable. And then we have to work out whether we divide it to 2-3 groups to say 50 odd questions or something like that. Because for any resource person who is as such is busy
Yeah.
to load extra, he can give you questions and model answers that we can expect from him.
Yeah.
But to check rigorously so many question answers is going to be difficult. So we have to work out, and Aditi can give us a feedback whether it is workable or not
Yeah,
workable.
sure. I
And this,
also will be happy to help, Dr. Rohini. You can let me know.
Yeah.
If
Please.
I mean, I was thinking that if downloading is a problem, then one person can. It will be cumbersome, but one person can download for each lecture. Just zip it up in a file and send a zip file to that resource person, so, or whoever is willing to sort of go through that answer. So I'll help in whichever way I can. Not
and
Yeah.
that Google Form solution is good so that we have within a given time frame only we receive the answers,
Yeah.
so that follow up becomes easy.
And also, Dr. Aditi is not only today's speaker, but also part of the organizing committee members, right?
No,
So
not really, sir.
she
All the
can,
running around was done by Rohini. She has
whatever, but we can always help.
tirelessly worked to make sure that this
I know.
functions smoothly, so as smoothly
Yeah.
as it is going.
Yeah,
So
but
I
you
just
can-
do whatever
Yeah, you
little
can-
I can help, I do that.
Sure. So you can always help from inside whenever
Sure.
possible. Yeah.
Little
So
help is most important.
right.
Critical little help helps a lot to
Yeah,
the
exactly. And also, Dr. Mohan had offered that he will use his volunteers also for some date. He mentioned that till there he had some volunteers who can help in evaluating, but he has, I think, discontinued now. He's not there today. So we can also ask him how many answer sheets he can take up. But I think first
Yeah.
we need to download all the answer sheets at one place and then share the link.
Sir, and you include Sahai sir's mail ID in the SAMA group so that he can
Okay.
receive.
I hope I'll check because
I will send you the mail ID from which he is actually
yeah,
mailing.
Gmail ID, I think, because his IITM ID may not be valid. I don't know.
Yeah, maybe because of that.
It was his IITM ID, it was included in the beginning, but that can be changed.
Sir, and also I would like to request if SVS Ramakrishna, he has already confirmed, but can we again send him the poster and
Okay, yeah. We need to also now check with the people, EC members who will deliver the welcome address for the next lecture or not. Because anyway, Naksim Muradi could not come today, so we'll check whether he can come next week.
yes.
Similarly, Singhe Dorji also could not come, so we'll check whether he can deliver later on. I mean, there are many things which we need to do I'm not sure why Maldives is not responding, whether all our mails are going to his spam box or something like that. If somebody has got the phone number, we will have to talk to them personally to find out
Yeah,
whether they're all those things. So anyway, we have to do all those things.
I may be
one
not
by one.
available on 29th, so I will request some of the ECT member to take up everything.
Yeah. I think I see that some of our ECT members are not regular nowadays, like Dr. Swagata, Dr. Mili, Dr. Lakshmi Kumar. I mean, they are all active members, but for some reason or other. I mean, earlier also for delivering this, moderating the question answer session or delivering the vote of thanks, one of the ECT members used to
Yes.
do that. But I see that either they are not asked or they are not announced. There's a
No,
silence.
there was a list already Google form shared, and whoever is ticked there, their name is being put in the poster.
I think we need to pressurize, otherwise people will not come forward themselves.
Maybe you can do that, sir.
Because if you just leave it for for their freedom, then probably people are busy, I mean, so
Yeah,
unless
that
they
is the reason.
unless they are
Yes.
pursued again and again, they won't come forward. So probably that we'll have to take care of, because now I see that only your students like Ashwin and Mrinal are
Yeah, at the
doing.
last moment, I don't want to. I
Yeah,
mean,
exactly.
so that is.
So therefore, probably we'll have to give this message every week on the ECT group. Like, in radar group, the earlier you might have seen, the people they were given the message that who is going to moderate the question answer, who is going to deliver the vote of thanks, etc.
Sir, then poster will be ready only on the morning of.
Oh,
Let's not get into it now.
This is
Yes.
also another limitation. Yeah.
Yeah.
But anyway, tentative poster can be shared on before like Monday, Tuesday, which can be again updated later on Thursday and Friday, things like that.
Okay.
Right.
Okay, then I will end the meeting and we can share other discussions on ECT group, sir.
Yeah.
Okay.
Thank you very much.
Thank
Okay,
you.
thank you,
Bye.
sir. Yeah.
Thank you, Dr. Rohini. Thank you, Das sir. Thank you, Tagi sir. And thank you, Ashwin and Mrinal, for always